Welcome to our fourth lesson. Today we will talk about the current divider and after that about measurement devices and measurement techniques. Okay, let's start with the current divider. We can use the current divider when we have a network of parallel connected resistors. Here I express them with their conductivities because it's more convenient for us. Okay, and if a current flows into that parallel connection and we want to know a current flowing through a special resistor in that network, we can use our current divider rule. Okay, I will show you how it works. So all the resistors are connected in parallel, and that means that we have the same voltage drop at every resistor. And we can express this voltage with the current flowing into it divided by the total conductance. So this is just Ohm's law. Okay, and we know that the total conductance is the sum of the single conductances because they are connected in parallel. Okay, but the same voltage drop is at our first resistor where we want to know the current flow through. So that means that the voltage drop at this special resistor or conductance is just the current through that element divided by its own value as a conductance. Okay, and now we can rearrange our equation, and this leads us to the equation for the current divider. I want to show you a special case. Often we express the element values by their resistances. And if we have a parallel connection of two resistors, then we can use another equation, and I like that very much, therefore I will show it to you. So we have a parallel connection of two resistors, and so we know that the voltage drop will be the same at both elements. And therefore we can say that the voltage is the current multiplied with the total resistance. And the total resistance, you remember, if you have two resistors connected in parallel, can be expressed like that. You multiply the two resistor values and divide by the sum of the two. Okay, and if we are interested in, for example, the first current in the first resistor, then the voltage drop there will be the same, and we can express it with Ohm's law. And again, we can rearrange this equation. You see, we can shorten R1, and it leads us to this equation. It nearly looks like the voltage divider rule for two resistors, but be careful here. There is in the counter of the fraction, the resistor, we are not interested in the current flow through. So keep that in mind, that in this equation, when you're interested in the current through R1, you have to put R2 in your counter. Okay, now let's talk about measurements. And let's start with a voltmeter, so an instrument which can be used to measure voltages. If we had an ideal device, then this device would measure the voltage drop between its clamps, and an ideal device would have no current flowing through it. That means that the inner resistance of an ideal device is infinite high. Okay, let's write down what I just said. Okay, and now let's think about a real voltmeter. So we said if we had an ideal instrument, then no current would flow through it. But a real voltmeter has a current flowing through it. And how could we model it? It's quite easy. We just add a resistor in parallel. So the current through the instrument flows through this resistor here, and you see it's the same current as here in the beginning, and we can calculate its value because we know the value of the resistor and we know the value of the voltage drop. The instrument displays it, and that means that the current through the instrument is the measured voltage divided by the inner resistance. Okay, so this here is the equivalent circuit of a real voltmeter. And yeah, if we use analog devices like this, then we would have an inner resistance in the range of 1 kilo ohm to 100 kilo ohm. And if we had digital devices like this, the inner resistance would be about 1 mega ohm. Okay, and if you want to measure voltage in a circuit, you add your voltmeter in parallel to the element where you want to measure the voltage at. And if we have a device like this, we can change the measurement range. And that means that we select which should the maximum voltage be we could measure. Okay, what happens in the instrument when we rotate that switch? Let's say we have a measurement device and its inner resistance is 1 kilo ohm and it is able to measure voltages up to 1 volt. Okay, then this would be the 1 volt connection, and the lower point is the common connection we use for all measurement range. We'll come to that in a minute. So I will call this here our core device. Okay, and how could we use it to measure higher voltages? For example, 10 volts. It's quite easy. We can just add another resistor here, and for 10 volt we take a 9 kilo ohm resistor, and then we have a voltage divider with 9 kilo ohm and 1 kilo ohm, and that means the 10 volt will divide by 9 volt and 1 volt. And that means the voltmeter will show its maximum value, and then we know, okay, the maximum value now means 10 volts. Okay, and we could go on. If we want to measure 100 volts, we add another resistor, and you see we have 99 kilo ohm in front of the measurement device, and the device itself has still 1 kilo ohm, and that means that this 100 volt will be divided by 99 volt and again 1 volt. Okay, and this here is our resistor network for measurement range expansion. Okay, so this is just what I said, and the interesting thing comes now. So let's have a look again at our network. If we use the 1 volt measurement range, our instrument has an inner resistance of 1 kilo ohm. And if we use the 10 volt measurement range, then our total inner resistance of the instrument is the 9 kilo ohm plus the 1 kilo ohm. So that means when we have the 10 volt measurement range, our device has an inner resistance of 10 kilo ohm. And at 100 volt measurement range, we have a series connection of all the three resistors there, and that means for the 100 volt measurement range we have 100 kilo ohm inner resistance. And therefore the manufacturer just says this measurement device has an inner resistance of 1 kilo ohm per volt. And this per volt means the selected measurement range. And therefore, you know, for this device here, when you have 1 volt measurement range, it has 1 kilo ohm inner resistance, 3 volt has 3 kilo ohm inner resistance, and so on. And I'm not sure if you can see it. On its back it says it has 1 kilo ohm per volt. Okay, let's talk about current measurement devices. They are called ammeter. So an ideal ammeter would be connected in series to an element. So if you want to measure a current, you have to open your circuit and put your measurement device into the circuit. And if we had an ideal ammeter, then the current would flow through it and there would be no voltage drop at the device. So it would have no influence to the circuit. So an ideal ammeter has no voltage drop. And that means it has an inner resistance of 0 ohm. Okay, but a real ammeter has an inner resistance, and we can add a resistor here, and we have to put it in series, and therefore the current could flow through the ideal device in our equivalent circuit here, and the voltage drop occurs at the inner resistance, and we can express it with Ohm's law. It's just the inner resistance multiplied with the actual measured current value. Okay, so this is the equivalent circuit of a real ammeter. And yeah, as I said, it has an internal resistance, and if you want to use it, you have to put it in series to the element where you want to measure the current through. Okay, and now let's say we have an ammeter and the inner resistance is 100 ohm for the measurement range 1 milliampere. And these are practical numbers. So if you want to measure 1 milliampere with this device here, it has an inner resistance of 100 ohm. So, okay, what happens here? In our equivalent circuit, the ammeter itself is an ideal device, and the voltage drop occurs at the resistance. So that means the voltage drop here would be the internal resistance multiplied with the current. So the maximum voltage drop that could occur here would be 100 millivolt. Okay, but if we want to measure 10 milliampere, what could we do? We need another path where 9 of the 10 milliampere can flow through. So what we do is we connect a parallel resistor, and we want 9 milliampere flowing through it, and therefore we can calculate its value. We want that when we have a voltage drop of 100 millivolt, that the current of 9 milliamperes flow. So we can use Ohm's law, and this leads to 11.11 ohm. Maybe it's more catchy if we express the resistor values by their conductances. So in our core device, we have a conductance of 0.01 Siemens. And at our parallel resistor, we have the conductance of 0.09 Siemens. So you see, 90% of the current will flow through the parallel resistor and 10% of the current will flow through our measurement device. And if we want to measure higher currents, we could just expand our resistor network and add more resistors in parallel. And you see, for 100 milliampere range, then we would add another resistance, and this would have only 0.9 Siemens. So you see, we have 0.99 Siemens in parallel to our instrument and 0.01 Siemens in our measurement device itself, and that means that 99% of the current flows through the resistor network and only 1% through our device. Okay, so yeah, what I said, our real ammeter has an equivalent resistance of 100 ohm when it measures 1 milliampere, and if we want to measure higher currents, we need a parallel resistor network. Okay, and here in our example, we had internal resistance of 100 ohm in the 1 milliampere range and 10 ohm in the 10 milliampere range and 1 ohm in the 100 milliampere range. So, and we have always, when the maximum current for our measurement range flows, we will always have the same voltage drop at the device. In our example, the 100 millivolts. And therefore, the manufacturer just tells in its manual that this device have a maximum voltage drop of 100 millivolt. Okay, so let's talk about how we could use these instruments. For example, let's discuss how we could measure values of resistors. You know, at a resistor, Ohm's law is valid. That means if we know the voltage drop at a resistor and the current flowing through it, we could calculate its value. Okay, and if we had ideal measurement devices, we could just measure the voltage and the current at the same time, and therefore if we want to identify the resistor Rx here, we just could divide the voltage and the current by each other, and then we have the resistor value. But our problem is that we don't have ideal devices. And now I will show you what we can do about it. So let's discuss this circuit. Here we measure the current correctly. And what we want to know is the current through our unknown resistor, and we want to know the voltage drop here. And then we would know that the resistor value is just Ux divided by Ix. Okay, and what do we measure? We measure this voltage here and we measure this current here. So you see, the current we measure is exactly the current through the resistor. Therefore, this chapter is called Measurement the Current Correctly. And okay, but our instruments have internal resistances, and that means our voltmeter looks like this and our ammeter looks like this. And that means we have an additional voltage drop at our ammeter. And the voltage drop is, we discussed it before, the measured current multiplied with the internal resistance of the ammeter. And what does that mean for the measured voltage? That means that we want to have Ux, but what we measure is the voltage drop Ux plus the voltage drop at the inner resistance of the ammeter. And therefore we have to calculate the value of Ux with Kirchhoff's voltage law, and then our equation for Rx looks like this. So, and if we know the value of Ra, we are able to calculate the exact value of Rx with this circuit here. We could build the circuit the other way around, so this time we measure the voltage correctly. Again, what we need is the voltage at the unknown resistor and the current, and what we measure is the voltage here. So you see the voltmeter and the unknown resistor are in parallel, so you measure exactly the voltage at the resistor. And we measure the current over here. And you already see it would be the current through the resistor, but also through the voltmeter. And if we add the inner resistors of our measurement devices, you see we have an additional current here. We can calculate it with Ohm's law. It's the measured voltage divided by the internal resistance of the voltmeter. And that means for our equation for calculating Rx that we have to use Kirchhoff's current law to calculate the correct value of Ix. And then the equation looks like this. Okay, maybe this have been a bit confusing, but I will show you in the next video an experiment, and maybe then it's more obvious what we were doing here.